we'll be talking about exponential functions and their graphs. Now, an exponential function is made up of f of x is equal to a times b of x. And if it is a growth function, b is going to be greater than 1. Now for the parent function, we're going to assume that a is equal to 1. So I'm going to erase the a, because that's what we end up with. Now, for the parent graph, the only point that really well, not matters, but the only point that we know for sure for a parent graph is the y-intercept, and the y-intercept is going to be at 0, 1. Now, when we graph the parent graph for exponential growth, we begin right above the x-axis in the second quadrant, go through that y-intercept, and swoop up. It's kind of a steep increase depending on the value of b, which is the growth factor, and also depending on the value of what your coefficient a is. Now, let's talk about exponential decay. Now, that applies to things like bacteria being reduced because of an antibiotic, or amount of radioactive die-off, that kind of stuff. And it's the same parent function. We're going to assume that a is equal to 1, and it's still b to the x power. But this time for exponential decay, b is going to be between 0 and 1. It's going to be a fraction between 0 and 1, because it's going to go down. And the same situation applies here, in that we know the y-intercept, but this time we're going to begin large. We're going to begin up high and work our way down towards the x-axis. Okay. Now, looking at the graphs, you can see what the domain and range are, and they're going to be the same for both of the graphs. The domain for this graph is going to be all real numbers. It's all the values of x. There's nothing restricting it. And the range does not go below the x-axis, so y is greater than 0. Now the asymptote is the line that guides our graph. We can't touch it. The value for our parent graph can never be negative, and so that means we're never going to reach the x-axis. So therefore that is our asymptote, x-axis, or y is equal to 0. Okay, so we're going to graph this exponential function of y is equal to 4 to the x power. And it's going to have the basic shape like this, because it's a growth function. Now, the steps. We're going to make a table. And I provided a table with values that are good for these numbers. They're not always going to be these numbers. I picked these because I thought they would work well. So when you plug in -1 up here to the exponent, right there, you get 4 to the -1, which makes a reciprocal, which gives you 1/4. When you plug in 0, you get 1. 4 to the 1 power is 4. And I could have done 4 squared, but 4 squared is 16, and 16 doesn't fit on my graph. So I tried 3/2. And if you remember, 4 to the 3/2, I'll write it over here. The half is a square root. You take the square root, that's 2, and then cube it, that's 8. and that does fit on my graph. Second thing you're going to do is plot points. And so we're going to come over to the graph and put those 4 points on there. Sometimes you need 4 points, sometimes you don't need 4 points. Sometimes you can get away with 2 or 3. So I've got -1, 1/4, so about right there. And then 0, 1, which is what I told you for the parent graph. And then we have 1, 4. And then 3/2 8. So about right there. And we are not going to touch the x-axis and kind of swoop up like that. And that is our graph. Like that. Okay. And the third step I just did. We're going to draw the graph, connect the dots. Okay, make sure it's smooth and curvy. Now the domain, again, is all real numbers. The range, y greater than 0. And this is an example of growth. And the reason I know that is according to my rule, my b is equal to 4, and that's greater than 1. And that's why I know it's a growth function, that and it's growing as you move left to right. So let's see what happens when we add a value in for a that's not 1 and we add to our function. Make sure when you enter this that you raise the 4 to the power first before multiplying by 5. Don't make it 20 to the x because that is not correct. And so when we graph this, we are going to have, I need to zoom in a little bit so I can find my points. So I've got -1.5 and about 2.5, so that's about right there. We'll call that good. And then we have -1 and 3.25, so about right there. And then our y-intercept is 7, 4, 5, 6, 7. And then at x equals 1/2, we have 12. And I believe that is right here at the top. Now, before you graph it, let's take a look at this. That plus 2, we learned before, if you add 2 to a function, it moves up 2. Okay? And the effect that this has is on the asymptote. The asymptote is now not the y-axis. It is now 2 above that. See, the asymptote is now as y is equal to 2. So we're going to start just above the asymptote and move up. Like that. The domain doesn't change. It's still all real numbers. And the range, yes, it is greater than 0, but it's greater than the asymptote, and that's what we're going to base our asymptote on, our range on. So y is greater than 2. And this is a growth function because our growth factor is 4, which is greater than 1. Okay, now let's look at an example of this one right here. We've got y is equal to 2/3 to the x power. Now, when we're making our table, if I have 2/3 to the -2, now that means I'm going to flip it over and make it a +2. So my y value is going to be 9/4. And if I do -1, we just flip it over. And that gives me a 1, and I get 2/3. Now, are these real pretty values to graph? No. But this is what happens when a lot of times when you have exponential decay. And so we're just going to do the best we can when we're graphing these. So I'm going to zoom in a little bit so I can see where my values are. So I've got -2 and 9/4. Now 9/4 is 2 1/4, so we'll go right here. And -1 3/2, and since it is decay, it should be descending. It should be going down right there. Now those 3 points probably would have been good enough knowing that my asymptote is the x-axis, but it never can hurt to have more points. So we've got our points plotted, and we can now connect our dots. Remember, it's going to be kind of steep, like that. And let's talk domain and range. And the asymptote, I just gave that away to you. That is the x-axis. Remember, that's a line you can't touch. It just shows you where you can't go, kind of like an electric fence for a dog. Your domain, all real numbers, that's nothing new. Your range, y greater than 0. And this is an example of decay. If you go back and look at your original problem, b is equal to 2/3, and that's between 0 and 1. Okay, I went ahead and filled in the points for you. What you're going to see is something we haven't seen before, which are negative values for y. And as you can see on the graph, I adjusted where my x-axis is. And the reason everything's going to be negative at this time is because of this negative coefficient. We've learned in graphing before that a negative causes our problems to reflect over the x-axis. It just flips it over, and so that's why the change. So I'm going to plot some points. Nope, that's not -12 down there. That's 13. So, let me see. -3. That's teeny tiny. Zoom it in. And -3/4. And then -3/16. Now my asymptote is my x-axis. I'm going to start way down here, connect this the best way I can, and not touch the x-axis. This one is not translated up or down because I don't have any values adding on to my function this time. So now my domain, it's still all real numbers. I'm just going to write the R. The range this time, though, look at what the y values are. What is the relationship to the asymptote? The asymptote is the x-axis, but it's not going above it, so y is not greater than, so now y is less than. And this is an example of decay. And that is because of this, the b is between 0 and 1.